Welcome to summer practice exam 2C. Okay, in this question we're comparing 5 different molecules and we're looking at them all at the same temperature, 100 degrees Celsius. So if we're considering the absolute entropy of a molecule, the first thing that we want to look at is the molecular complexity, aka the number of atoms. So, the more atoms there are, the more dynamic a molecule is. Because remember, atoms are not stuck in space. Bonds can contract, they can expand, they can wobble, molecules can rotate. So, we're going to eliminate choices A, B, and C, because those ones only have 5 atoms, which leads us with D and E, which each have 1, 2, 3, 4, 5, 6, 7, 8 atoms. Okay, so after looking at the molecular complexity, we're going to look at the mass, because remember, heavier atoms have more shells of electrons. More shells of electrons means more absolute entropy. So between these two, choice E has 2 bromines instead of 2 chlorines. Bromine is significantly heavier than chlorine. It has more, it has an additional shell on it. So this is going to be our greatest gas phase entropy molecule of these possible choices. This question poses, in which of the following reactions does Kc equal Kp? And in order to answer this, we need to consider the relationship. Kp, the equilibrium constant with respect to partial pressures for reactions involving gases, is equal to Kc, the equilibrium constant with respect to concentrations, times RT to the delta N, where this is the one time in the course we're going to be using this version of the gas constant R, 0.08206 liters atmospheres per mole Kelvin, because this is a PV-nRT relationship here. And delta N is the moles of gas in the products of the reaction minus the moles of gas in the reactants. So if we're trying to get Kc equal to Kp, what does that mean? We want the whole RT to the delta N to equal. So if we want Kp to equal Kc, that means that we need this whole RT delta N term to equal 1. How can we most easily get RT to the delta N to equal 1? Well, this means that we want delta N to equal 0, because anything to the 0th power is 1, and then that will basically, in effect, turn this all into 1, and then we'll have Kp equals Kc. The only reaction where this holds true is reaction E, because we have 2 moles of gas in the products and 2 moles of gas in the reactants. Alrighty, in this problem, we're trying to relate an initial amount of, in this case, reactants, with the equilibrium amount. So whenever we're trying to relate the initial amount and the equilibrium amounts, when in doubt, ice it out. That's right, we're going to use an ICE data table. So with the ICE data table, the key is to plug in the values that we know and then to fill out the rest. So let's see what we've got here. We're told that we're just starting with only 9 atmospheres of NO. So let's plug that in. We have our 9 there. And we can infer, unless told otherwise, that we're starting with 0 N2 and 0 O2. Okay, so now what is the change going to be? Well, the only direction that this reaction can move is to the right, because there are no products to convert back into reactants. And then we want to consider that this is a 2 to 1 to 1 ratio. So since we don't know what the equilibrium amount is, we're going to use a variable. We're going to say minus 2x here. For the N, it's going to be plus x, and for the O2, it's going to be plus x. Okay, which leads us with, at equilibrium, 9 minus 2x, all we have to do for the equilibrium values is just add together the initial and the change. 0 plus x is x, and 0 plus x is x. Cool. Now, we are halfway to solving our ICE table problem. Now, remember, in order to completely solve these problems, we need to pair this with its equilibrium expression for great results. So, our equilibrium constant is equal to products to their respective coefficients, which is just 1 in both these cases, over reactants, so the pressure of nitric oxide squared. Now we'll plug in the values that we have from both our equilibrium constant and from the equilibrium line of our data table. So we get x times x over 9 minus 2x squared, but we can simplify x times x and make it x squared. Cool. Now let's take the square root of both sides. When we do, this simplifies a little bit. And we get 4 is equal to x over 9 minus 2x. So remember, there are cases that you could encounter theoretically that would involve needing to use the quadratic formula. But in Chem 112 world, we're never going to need to do that. We'll always have a way of simplifying to avoid that pesky quadratic formula. Now then, let's multiply the 9 minus 2x through. Factor that 4 through. We get 36 minus 8x is equal to x. Add 8x to both sides. Now all we have to do is divide both sides by 9. And we'll end up getting that x is equal to 4. Cool. So we are so close to the answer. Then we just need to make sure that we answer the question that's given. What is the partial pressure of oxygen? So oxygen, if we look at the equilibrium value, is equal to x. And so all we have to do is just say, well, we know that that's 4 atmospheres. And we have our answer. In this question, we're looking for the expression for the equilibrium constant for this particular reaction. And equilibrium constants for gases can be done in either concentration or in pressure. But here, all of these answers are in terms of concentration. So Rk is going to equal, well, if we look at our product, it's a solid. Do we incorporate solids into our equilibrium expression? No, we do not. So we'll replace it with a 1. And then we have the concentration of CO2. And then, calcium oxide, also solid. So that's going to be replaced with a 1, but we don't need to write in the 1 because saying 1 times anything else is redundant. And we're done. Okay, so this was actually created through our ammonia synthesis app on the ebook. And it's monitoring the reaction of hydrogen plus nitrogen yields ammonia under a certain set of conditions at a given temperature. And we wanted to know what is the value of Kc under these conditions. Okay, so first let's look for when equilibrium is established. Remember, equilibrium is when the forward rate and the reverse rate, how do they relate? Well, they're the same. So equilibrium is established when there's no more fluctuation in concentration. And we can see here it's actually denoted by this dotted line because at this point all 3 concentrations, the N2, NH3, and the H2 all remain consistent. So this is where equilibrium is established. So we're not going to use these values over here. These are our initial concentrations. Not going to help us answer this question. What will help us answer the question are the equilibrium values that are established, which are right here. Okay, so always write out an equilibrium expression, which for the Haber process is K is equal to the concentration of ammonia squared over the concentration of nitrogen gas times hydrogen gas cubed. Cool. All right, now we just need to plug in our values. There we have them, and now let's do our calculation and see what we get. This ends up equaling 0.376. This question wants to know which of the following reactions leads to a decrease in entropy. So the most important factor to consider when looking at entropy change of a reaction is the phase of matter. So solids have the least entropy, then liquids, then gases. And for our purposes, aqueous things, they fall in, generally speaking, between liquids and gases. We'll actually see that some aqueous species help coordinate and create more organization in their environment. But for our purposes for this unit, let's just assume that aqueous species have about the same absolute entropy as gases. The other way that we can increase entropy is by going from fewer moles of stuff to a greater number of moles. So since we're looking for a decrease in entropy, we're going to look for a reaction that either has our reactants going from a gas to a liquid, or a gas to a solid, or a liquid to a solid, or we're looking for a reaction where we go from more moles of stuff to fewer moles of stuff. So which one matches that? This one right here, we're going from 3 moles of gas to only 2 moles of gas. This question asks us about what is the situation when Q is less than KEQ. So remember, Q is the product-reactant ratio that we have, whereas K is the product-reactant ratio at equilibrium. It's the product-reactant ratio that this reaction is trying to get to. KEQ is a constant for any given reaction at any given temperature. Q, on the other hand, can be any number theoretically from 0 to infinity. If Q is less than KEQ, that means the product-to-reactant ratio that we have is less than the product-to-reactant ratio that we want, which means this reaction will move forward spontaneously. So this means that we will have a negative delta G, a spontaneous reaction, and it can do work. So which of these are true? Well, the reaction can perform work. Any spontaneous reaction theoretically can do so. And the reaction proceeds in the forward direction. Also accurate. The reaction has a positive delta G? No! That would be a non-spontaneous reaction. Now, if Q was greater than KEQ, that means the product-reactant ratio that we have would be greater than the product-reactant ratio that we want. In that case, a reaction, as written, would have a positive delta G, could not do work as written, and would instead proceed spontaneously to the left to make more reactants. Our final scenario is if Q is equal to KEQ. Well, if Q is equal to KEQ, what does that mean? What chemical state are we at? Dun 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 dun! We're at equilibrium! Woo! And at that point, delta G is not positive nor negative. It would be equal to 0. So our answer for this problem went on a little bit of a segue here. Not really a segue, just kind of more in-depth. But when Q is less than K, 1 and 2 here are true. 3 is not true. So we have here a boss fight problem, because we're trying to find delta G for this particular reaction. Okay, so here's our reaction. It's the dissociation of acetic acid. Neat, it's what gives vinegar its punchy taste. We're given a KEQ. Alright, good to know. And then finally we're given this nice array of concentrations. Alright, so anytime you're asked to find delta G, and you're given concentrations that are other than 1 molar, if we have any concentration other than 1 molar, are we under standard conditions? No, most assuredly not. We have non-standard concentrations. Whenever you have non-standard concentrations, this is the equation that you're going to need to use. Delta G equals delta G standard plus RT times the natural log of Q. This is the equation you'll always use to find delta G when you have any concentration other than 1 molar or 1 atmosphere for a partial pressure. Now then, what do we have? Do we know temperature? Well, yeah, it's 298 K. Do we know R? That's a constant. Yes. Do we know Q? We can easily find it. However, wait a minute, delta G standard. Do we have delta G standard? We do not. But do we have something that's directly related to delta G standard? Indeed we do. Whenever you have KEQ, you can find delta G standard. Likewise, if you have delta G standard, you can find KEQ. These are both constants for any given reaction at any given temperature. So we can use this to find our delta G standard using the equation delta G standard equals negative RT times the natural log of KEQ. So let's find our delta G standard here. Our value for R traditionally, we can see now if all of our answers are reported in kilojoules. So for R, I'm going to use 0.008314 kilojoules per mole Kelvin. Our temperature is 298 K. And our KEQ is up here, 1.8 times 10 to negative 5th. When it's all said and done, we'll end up getting delta G standard equals positive 27.1 kilojoules per mole. In the words of the great poet and philosopher John Bon Jovi, whoa, We're halfway there. Now we need to find our actual delta G with these concentrations. I would advocate for whenever you have to find Q, always write out an expression for Q. So Q is going to be equal to our concentration of products over reactants. So Q is equal to the concentration of CH3COO minus times H plus. This is all divided by CHO, CH3COOH, acetic acid. All right, let's plug in our values and see what we get. So there we have our products. On our reactants, ooh, this is glacial acetic acid. This is pretty much as concentrated as you can get acetic acid. It's 18 molar. So we end up getting that Q is equal to 5.56 times 10 to the negative ninth. Now, before we mathematically solve for this, I want us to think conceptually about what this means about which way the reaction would need to go in order to reach equilibrium. So we have our value for Q now. How does Q, the product-reaction ratio that we have, that we just solved for down here, compare to KEQ, the equilibrium constant, up here? So Q, we can see, is decidedly less than KEQ. Whenever Q is less than K, we know, this goes back to the previous problem that we did, which way does the reaction need to proceed in order to reach equilibrium? It would need to go forward, which means we can predict here that delta G will be negative. And indeed, we will see that's the case. So now let's plug in and solve for delta G. So using this equation up here, delta G is equal to delta G standard, which we solve for, 21.7 kilojoules per mole, plus RT, times the natural log of Q, which is 5.56 times 10 to the negative ninth. So I almost like to think of this as the correction factor to make up for our value of Q. Let's see what we get. So delta G standard is equal to 27, or sorry, we have delta G is equal to our delta G standard, 27.1 kilojoules per mole, plus, and this whole thing ends up equaling negative 47.1 kilojoules per mole. So now we add those two together, and we end up getting that delta G is equal to negative 20 kilojoules per mole. Alright, in this problem, Rick Cat, who's a famed scientist, trying to make some nitric acid, HNO3, using this particular reaction. And we're given a bunch of initial concentrations, and we're given an equilibrium concentration. We're trying to find KEQ whenever we're trying to relate an initial amount, an equilibrium amount, and our KEQ, when in doubt, ice it out. So let's write our reaction. We have two nitrogen dioxides, NO2. We've got hydrogen peroxide, H2O2. It's turning into two nitric acids, HNO3. And then we're going to write out ICE and fill out everything that we know. So we're starting off with 8 molar of NO2, we'll fill that in, 5 molar of hydrogen peroxide, H2O2, and 4 molar of HNO3. Now, there's essentially two flavors of ICE table. There's ones where we're given an initial amount, and we're given no information about the equilibrium amounts, and we need to use variables. But in this case, we're actually given the equilibrium amount of one of these chemical species. We're told that the NO2 drops down to 2 molar. This is significant because if you know the initial amount of something and the final amount, you can always find the change. And if you know the change in one thing, you can find the change in everything else. So the change, if it went from 8 to 2, is negative 6. We can also see that for every 2 of these, we lose 1 H2O2. So it's going to be minus 1/2 of 6. And for every 2 of these, we gain 2 of these. So this is going to be plus, because it's our products we're losing from the reactant side, which means we must be gaining over here. And it's going to be an equal amount, plus 6. So our equilibrium amounts are, we've got 5 minus 3, which is 2. And we've got 4 plus 6, which is 10. Now we have our ICE table figured out. We're trying to find our equilibrium constant KEQ, so let's write out that expression. KEQ is equal to our products to their respective coefficients, so HNO3 squared over reactants. NO2 squared times H2O2. Now let's plug in our values. So it's equal to equilibrium. We've got 10 of the nitric acid. So 10 squared over 2 squared times 2, so 2 cubed. And we'll end up getting 12.5. Alright, in this question, we have to figure out where equilibrium is and what line represents delta G standard of the reaction. So delta G standard of the reaction is equal to the free energy of formation of the products, sum of the free energy of formation of the products minus the sum of the free energy of formation of reactants. So it is described by line segment A. This is the difference between the products and reactants. And we can see here that there's a positive delta H standard. The next part says what point represents equilibrium. So equilibrium is the lowest point on this graph. It is the minimum for delta G. So it can be found here at point D. It should be noted that for any reaction that has a positive delta G standard, KEQ will always lie toward the reactant. So here we can see if this is a 50-50 mixture, our equilibrium would be right there. We can see that our equilibrium, lies more toward the reactants. If delta G standard was negative, then our equilibrium would lie more toward the products. This question asks, under which of the following sets of concentrations will the reaction below proceed spontaneously in the forward direction? So, if a reaction is going to go spontaneously forward, that means that we want Q to be less than KEQ. So let's try choice A and see what that does. For a question like this, always write out the equilibrium expression. So Q, our product-reactant ratio, is the concentration of C over the concentration of A and then B squared. Okay, so now let's fill out the numbers for A and see if Q is less than K. So our values are C is 1.4, A is 0.6, and then B is 0.2. And we end up getting 58.3. So in this situation, Q is decidedly greater than KEQ because 58.3 is objectively larger than 26 RK, which means this reaction would make more reactants in order to reach equilibrium. We have a positive delta G as written, so this is not going to proceed spontaneously forward. Now let's do it for answer choice B. For B, the concentration of C is 0.6 molar. Not a lot of products there. For A, it's 1.5 molar. And then for B, it is 1.2 molar. When we do this calculation, we end up getting that Q is equal to 0.278. Now, if we look in this scenario, Q is decidedly less than KEQ, which is exactly the situation that we were trying to find here. So this is going to be our answer. You can always tell which way a reaction is going to go by comparing Q with K. This reaction says for the elementary reaction A turns into B, the rate constant for the forward reaction is K sub F, and the rate constant for the reverse reaction is K sub R. One expression is equal to the equilibrium constant KEQ. So remember, at equilibrium, how do our forward rate and our reverse rate relate? They are the same. So what I'm going to do is write a forward rate law for the forward reaction. So K sub F, it's elementary, so we can write it in terms of we can write a rate law based on this. And at equilibrium, the forward rate and the reverse rate are the same. So this is our forward reaction. Again, the forward reaction has a rate constant K sub F, and the reverse reaction has a rate constant K sub R. Okay, so K sub R times the concentration of products. Okay, so remember, an equilibrium constant is equal to the concentration of products over reactants. So we want to rearrange this expression up here in order to match that. So in order to do that, we want to get B over A. So I'm going to divide both sides by A. That effectively cancels out A over here. And then in order to isolate B, we need to divide both sides by K sub R. Which will cancel out K sub R over here. And we end up getting Kf divided by Kr equals B over A, which again is equal to our equilibrium expression. So it's going to be K sub F divided by K sub R. In this problem, we're looking at adenosine triphosphate, a very important molecule. The bonds in adenosine triphosphate are high energy, and using these molecules, by having them dissociate, they can release that energy and help fuel other processes. So the negative Delta G standard is really, really important for helping to facilitate other reactions inside the body. So how do we relate KEQ and Delta G standard? Well, we can use this expression. Delta G standard equals negative RT times the natural log of KEQ. So all we have to do is plug in our values. There we go. And we're trying to solve for KEQ. So at this point, Kelvin cancels out. Let's divide both sides by RT. We're going to divide both sides by R and T, so and the negative sign. So we'll divide both sides by negative 0.008314 and by 298. We end up getting 24.6 is equal to the natural log of K. Then in order to get rid of the natural log, we need to use Euler's constant E. When we do, that will effectively cancel out the natural log, and we end up getting 4.93 times 10 to the 10th. Now it should be noted that depending on the number of significant digits you use, you might get an answer that varies a little bit from that in terms of precision. But you'll notice that none of the other answers are remotely close to the right answer of 4.93 times 10 to the 10th. Okay, so in this question, we're trying to figure out, we're looking at aluminum, and we're trying to melt aluminum. So first thing I would do is write out an equation. We are taking aluminum solid and turning it into aluminum liquid. Cool. Generally speaking, anytime you have a table of thermodynamic data, so anytime you're given the enthalpy, entropy, or free energy of either formation or the absolute entropy of any molecule, and you're trying to relate to a reaction, you're probably going to use the products minus reactants rule. Okay, so that's why an equation is very, very useful to help us with this problem. Now then, once we have our equation written out, now what we're going to do is use the products minus reactants rule in order to get the enthalpy change and the entropy change of this reaction. So, our delta H standard of this reaction, the standard enthalpy change, is going to be equal to the enthalpy of the products, 10.56 kilojoules per mole, minus the enthalpy of the reactants, which is 0. So, just equals 10.56 kilojoules. So this is indeed an endothermic reaction, as melting always is. Now we'll do the same thing, only we'll do it for our entropy. So our standard entropy change of the reaction will be equal to the entropy, the absolute entropy of the products minus the absolute entropy of the reactants. So we end up getting 11.22 joules per Kelvin, and indeed melting will always lead to an increase in entropy. Now, what we want to do is we want to figure out at what temperature this becomes spontaneous. So you think about reactions. If they have a negative delta G, they're spontaneous as written. they have a positive delta G, they're non-spontaneous as written. So the magic number where a reaction goes from spontaneous to non-spontaneous, or vice versa, is where delta G equals 0. That's going to be the temperature where this is an equilibrium process, aka the melting point. So, what equation relates enthalpy, entropy, and free energy? That's right. Delta G equals delta H minus T delta S. And you can have these standard signs in here because standard enthalpy and entropy changes for reaction don't change that appreciably with temperature. However, free energy, delta G, changes wildly with temperature, as temperature is one of the variables in this equation. So now what we're going to do is set delta G equal to 0 and solve for the temperature where this happens at. So we have 0 is equal to our enthalpy, which is 10.56 kilojoules, minus T, that's what we're solving for here, trying to find this temperature, times delta S. And notice delta S is in joules per Kelvin. This is usually how entropy is reported. So we're going to need to convert this into kilojoules so that our units are talking nicely to each other. This gives us 0.01122 kilojoules per Kelvin. Now we're going to add the T times 0.01122 kilojoules per Kelvin to both sides, and we'll get this. Then divide both sides by 0.01122 kilojoules per Kelvin. Kilojoules will cancel out, and we'll end up getting that T is equal to 941 Kelvin. Here we have another equilibrium question. We're studying gnatanic acid. Cool. Or gnatanic acid. Sorry, gnatanic acid. H2NTO3. Obviously very important. And now what we're going to do here is we're given the equilibrium concentration of H2NTO3. We want to find the relative concentration of O2. So what we're going to need to do is write out an equilibrium expression. So we have products over, and this is a solid, so we're not going to use it. And this is a liquid, so we're not going to use it. We're only going to use the O2. So if we know the concentration of everything at equilibrium except for one of the chemical species, and we know the equilibrium constant, we can find the concentration of our missing chemical species. So let's plug in everything. So we plug in our equilibrium constant, 409, and we plug in our concentration of gnatanic acid, which is 1.5 molar. And now we can solve for the concentration of O2. So we'll multiply the O2 through. We'll get O2 concentration times 4.09 is equal to 1.5. Divide both sides by 4.09 and we get our answer. The O2 equals 0.367 molar. This question says which of the following processes corresponds to a decrease in entropy. Okay, so to quickly go through our phases from most entropy to least entropy. Gases have the most entropy, then liquids, then solids. So, for entropy decreases, we're looking at a gas to a liquid. That process is known as condensation. A liquid to a solid. That process is known as freezing. And then finally, a gas to a solid. That process is known as deposition. So all three of these processes lead to a decrease in entropy. So freezing, check. Condensation, check. 2 and 3 only. Melting, sublimation, and evaporation, those processes lead to an increase in entropy. In this question, we have to figure out some information about the thermodynamics of the combustion of glucose. So, first things first, combustion. Anytime we see the word combustion, we know that our enthalpy change is going to be what? Positive or negative? That's right, this is always an exothermic reaction. It's always going to be a negative value. Then, we can look at our reaction to figure out if it's an increase or a decrease in entropy. So we're going from 1 mole of solid and 6 moles of gas to 12 moles of gas. Whoa! 1 mole of solid and 6 moles of gas to 12 moles of gas. We're looking at an increase in entropy. Finally, if we want to consider the temperature dependence of delta G, remember delta G is equal to delta H minus T delta S. Okay, and in order to make a graph like this, I like to think of extremes. So extreme number 1, let's set temperature equal to 0.00000000000004 Kelvin. So that means that if this is equal to practically 0, it's basically going to take this whole term out. And our delta G will be equal to whatever our enthalpy change is. Since this is negative, that means that if we're making a plot where delta G is on the y-axis and temperature is on the x-axis, at the 0 point, our free energy is going to be negative. And then what's going to happen to our delta G as the temperature increases? So now we want to consider that we're subtracting T delta S. And we want to think about what happens as T gets larger and larger and larger. So T has to be a positive value because it is an absolute temperature. We also know in this particular reaction that delta S is positive. So what happens as T gets larger and larger? This whole term becomes more and more positive. If we're subtracting an increasingly more positive term, what's going to happen to our value? It's going to get more and more negative. So as temperature increases, this value is going to go down. So the answer that matches this particular graph is choice A. In this reaction, we're given the equilibrium concentration of SO3, and we're trying to find Kp, and ooh, notice that Kp is bolded and underlined, and then it says, hint, make sure you're solving for Kp. That feels notable. Alright, so first let's come up with an expression for Kc. Kc is going to be equal to the concentration of our products, SO3, to the respective coefficient, which is squared, over reactants, but hey, this is a liquid, so it's not going to factor in. Okay, so we can solve for the value of Kc. It equals 1.75 squared, which is 3.06. Great, that's Kc. But are Kc and Kp, which is what we're solving for, equal? Well, no, because if we look at delta M, the number of moles of gas in the products minus the moles of gas in the reactants, the only time when Kp will equal Kc if there's an equal number of moles of gas in the products and reactants, which is not the case here. So our delta N is equal to 2 moles of gas in the products minus 0 moles of gas in the reactants, which is equal to 2. If delta N is anything other than 0, Kp will not equal Kc. So we need an equation. Do we have an equation to relate Kc and Kp? Yes, it is. Kp equals Kc times RT to the delta N. And remember, this is the one time in the course where for R, we'll use the gas constant version 0.08206 liters atmospheres per mole Kelvin. So Kp is going to equal that Kc that we solved for, 3.06, times R, 0.08206 liters atmospheres per mole Kelvin, times our temperature, which is 323 K, and then all this is to the delta N, which we solved for before. Our delta N is equal to 2. So now let's see what we end up getting. We end up getting that Kp is equal to 2,150. Alright, now we have a question about propane combustion. It's a very popular reaction for summer/outdoor grilling season. And we're trying to find out how much work this can do on a warm, sunny day at 30 degrees Celsius. So we're trying to relate enthalpy, so delta H, entropy, S, and work, free energy. That means we're going to need our ever-popular equation, Delta G equals delta H minus T delta S. This is always what we're going to use to relate enthalpy, entropy, and free energy. And remember, we can write the equation like this. We can also write it with the standard sign, since enthalpy, standard enthalpy, and entropy don't change appreciably with temperature. All right, but wait a minute. We're only given the information about the molecules here. So we're given the enthalpy of formation and the absolute entropies of all these molecules. But we need it for a reaction. That means we need the products minus reactants rule. So we're going to do the products minus reactants rule for both enthalpy and entropy. Then we'll have everything we need to answer this problem. All right, so our delta H standard for this reaction is equal to the enthalpy of our products. We've got 3 moles of our CO2, and CO2 is negative 394 kilojoules per mole, plus, and we've got 4 H2Os, and H2 is negative 242 kilojoules per mole. So all these are in kilojoules. So products minus reactants, I like to offset my products and reactants in brackets, just makes it easier to organize. So we have propane is negative 104 kilojoules per mole. There's only one of them. And there are 5 oxygens, but each oxygen is bringing a whopping 0 kilojoules per mole to the table. Again, these are all in kilojoules, which ends up giving us negative 2,150. Okay, now let's solve for the entropy change. Once again, we're going to do the products minus reactants rule, only we'll be using the entropy values. So our products are CO2 and H2O. And notice that, generally speaking, for entropy, we're looking at joules. Okay, so there are our products, and let's subtract from that our reactants. There we go. And again, these are also in joules per Kelvin. And we end up getting that the standard entropy change of this reaction is 103 joules per Kelvin. Now we have everything we need to solve for delta G. So we'll plug into our equation. Delta G is equal to our standard enthalpy change. There we go. Minus T, our temperature in Kelvin. So we have to take our 30 degrees Celsius and add to it 273, which ends up being 303 K. Cool. Times our delta S. Again, we want to report our delta S in like units. We could either turn our enthalpy into joules, or we can turn our entropy into kilojoules. Since our answers are in kilojoules, probably just easiest to turn our joules into kilojoules. And there we have that, and let's see what we end up getting here. And oh no, I've identified a calculation error. So this negative 2,000, let me go back and amend this. So this value here is actually equal to this, but I did not subtract the negative 104. So my apologies, this value should actually be negative 2,046 kilojoules. My apologies. So we'll replace that in our actual problem. So we'll get rid of the wrong number, put that in. Alright, now we're primed for success. So when we do this, we'll end up getting negative 2,077 kilojoules. So the negative, what does that mean? It means it's spontaneous, right? So if it's spontaneous, can it do work? Yes. And how much work can it do? Well, the maximum amount of work it could do is 2,077 kilojoules worth. Choice B. Alright, and the final question before we move into our Le Chatelier's principal gauntlet of destiny is we're manipulating K values, and we're trying to get this overall equation right here. So the first thing I always like to do is I like to ask myself, in our equations that we have data for, so equations 1 and 2 here, are our reactants and products on the side where we want them when we convert to our overall reaction? So for example, acetic acid, CH3COOH, do we want it to be a reactant in our reaction? Well, yes. Do we want Keq acetate to be a product in our reaction? Well, yes. So this reaction looks like everything is lined up on the correct side. Oh, but if we look at this reaction, it's a very different tale. H2O is a reactant in this reaction. It's a product in this one? What? But and wait, hydroxide is a product in this reaction, but we want it to be a reactant. Oh my goodness, everything's all backwards. That's okay. We can flip that reaction around. When we flip this reaction around, I'm going to call this reaction 2'. So we have H plus OH minus yields water. Okay, and then what happens to our KEQ? So our KEQ of this is going 1 divided by 1 times 10 to the negative 14th. We have to take the reciprocal. And when we do, we end up getting that it's actually 1 times 10 to the positive 14th. Okay, so now just to make things a little bit easier to work with, I'm actually going to cross out this reaction since we're not going to be using this reaction. We have a new and improved one we can use. Now, in order to get this overall reaction that we have below, we'll notice when we combine these two reactions together, what cancels out? Well, there's an H plus that cancels out. And everything else looks good. So we'd end up with CH3COOH plus hydroxide yields water and acetate, CH3COO minus. So now what we're doing is we're combining reactions 1 and 2'. Remember, whenever we combine two reactions, how do we get the new KEQ? We multiply together their K values. So, call this KEQ double prime is going to be equal to 1.8 times 10 to the negative 5th, our first KEQ, times our 1 times 10 to the 14th from our second reaction, the one that we actually had to flip around. And when we do, we'll end up getting that the value of our new KEQ is equal to 1.8 times 10 to the 9th. And finally, it's time for our Le Chatelier's Principal Gauntlet of Destiny. Rocket Edition. We want to see how these changes will affect the equilibrium of this reaction. So it's exothermic. First thing I would always do is include heat as a reactant if it's endothermic or as a product if it's exothermic. So since this is exothermic, I'm going to just write in plus delta. And again, delta just means heat. Because we can think of heat as being a product here because exothermic means energy, heat is exiting from this reaction. Okay, now let's go through each of these and analyze. Okay, question 21. H2O gas is removed from the reaction vessel. So if we're removing H2O gas, if we're at equilibrium and we remove products that are either gaseous or aqueous, that means there's not enough products anymore. So Q would no longer equal K, which means this reaction would shift to the right in order to get back to equilibrium. What if the temperature is decreased? It's like we're removing heat from this reaction. Well, again, heat's kind of like a product, and even though this is a simplification of thermodynamics, it's one that works really well with Le Chatelier's principle. So if we're losing products, we actually need to shift to the right. Up next, we have more CO2 gas is added. So CO2 gas is a product. If we're increasing the amount of products, that means that suddenly we have too many products, so this reaction would have to shift to the left in order to reestablish equilibrium. The next one says more calcium carbonate is added. Now notice this is a solid. Do solids affect our equilibrium, our value of Q, and our comparison of Q and K? Will adding or removing a solid shift the reaction? Nay. So this is going to do neither. So the final question is, what happens if our value, or what happens if our reaction vessel, the volume is decreased? Now remember, if you decrease volume, that means that you end up with an increase in pressure because smaller environment for the gases to move around means more collisions. Okay, so the Chatelier's principle says that if we artificially up the pressure, the reaction will shift to the side that will help alleviate the pressure, that will help remove some pressure. So the reaction will shift to the side of the reaction that has fewer moles of gas. Which side is that? So we have 0 moles of gas on this side. we have 2 moles of gas on this side, the reaction then would shift to the left, because that shift would help alleviate the pressure, because we'd be removing gaseous molecules and turning them into solids and liquids which do not exert pressure. So this will cause a shift to the left. Thank you very much for watching, and here's your friendly reminder to dominate the exam. If you felt comfortable doing these problems, that means you have mastered equilibrium and thermodynamics, and you will do very, very well. Should do very, very well. So go forth confidently and show that exam who's boss. Keep up the great work. Thank you for your time, and have a wonderful day.